Welcome everybody to our second Cygnus series lecture. Since we've booted back up again, I'll give you a preview of our total schedule in a little while, but just wanted to do some introductory stuff. And you know that I can talk about the Adirondack Sky Center and Observatory for hours on end, but I won't do that tonight. Just give you a little bit of the preview, and you can always find out more information by contacting our office, which I'm going to put our email address and our phone number in the chat at the moment, so you'll have that. If you have any questions at a later date or anything, don't ever hesitate to call or email. And of course, our website located there. And also, we have quite a presence on social media and our YouTube channel, which is where you'll find the recording of Jeff's talk in a day or two. I'll get that edited and put up there for everybody to see. So with that, welcome. You should be seeing the Cygnus Lecture Series icon now, and you'll notice that that's brand new. We've really revamped a lot of things in the past year. Really post-eclipse, I would say. That's the way I think of the world as in terms of eclipse and post-eclipse. So we've rebooted the Cygnus Lecture Series, and just to give you an idea a little bit about who we are, we are the Adirondack Sky Center and Observatory. We're located in Tupper Lake, and of course, the reason we're located in Tupper Lake is because it's some of the darkest skies in the Northeast, and we are right in the center of that red circle there, the heart of darkness, as you've heard me say many times before. With all of the light pollution around us to the north, south, east, and west, visitors regularly come to Tupper Lake for the Sky Center specifically. And that's not necessarily a new phenomenon, but it's a growing phenomenon. Whenever we do public observing programs, more and more people are telling us that they're here because of us, which is really nice to hear, and because of our dark skies. And I'll share a little bit more about dark skies in a few minutes. But our purpose is really to kind of provide perspective on the universe and space exploration and all things having to do with things not on this planet necessary. We try to do as much immersive experience as we can, including our planetarium, our public observing events, any programs that we do. We really try to hit home that we're really trying to demystify the universe. And as our colleague Eileen O'Donoghue has coined, we are interested in the very first wilderness, the wilderness above. Everything on Earth came from out there, and we wonder at that and in amazement and appreciate it, and we want to help others do that as well. We have two locations, one on Park Street. This is our main office, our astronomy hub. In here, we have planetarium programs. We have classes that we do. But we have a series of programs, public observing, private parties, large events, astrophotography conference, and just a ton of outreach, visiting schools, doing summer programs. Simon, our outreach coordinator, has created new programs under the umbrella of Cosmic Explorers. So the first rocket lab took place this summer, and we're working on a coding program that you'll be hearing more about in the coming months. Of course, we take our Star Lab all over the North Country. Literally, I think we've been to every corner of the Adirondacks so far, and perhaps even outside of the Adirondacks. There was a school so far north in the Adirondacks that I'm pretty sure it was in Canada. And the way that school district works is that it's on Canadian land, but it's part of the New York State school system somehow. I don't really remember exactly the specs on that, but it was really far north. We have our annual astrophotography conference, and I see a lot of you from that are here. Very nice. In our office right now, the result of previous astrophotography conferences is our Universal Visions astrophotography exhibition. These very high resolution, large format, literally 3 feet by 4 feet in size, in high resolution. Just a phenomenal thing to see. So if you're in the area, stop in 68 Park Street during business hours, and have a look at those. It's really stunning, all from members of our astrophotography conference. And by and large, all of them shot right here in Tupper Lake. And here's our planetarium, the Star Lab. It's busting at the seams. You can see there, it's barely supported by the ceiling there. We can just about get it in there. But we have programs that we run on a regular basis on Thursday afternoon or Thursday evenings and Saturday mornings, and special showings of produced video and some very other specialized programs that we do as well. You're, of course, here for the Cygnus series tonight, and this is our schedule for the coming months. We're scheduled right through the end of this. I refer to it as the school year. It's an occupational hazard, having been a superintendent for so long. June is the end of the school year, so we're programmed pretty much out through then. And tonight, of course, we're here with Jeff. The one exception to the first Tuesday of the month is that in a few weeks, our colleague and board member Eileen O'Donoghue is going to join us and take a look at the first look at the Vera Rubin Observatory. So that'll be very exciting. We do our private parties. We've had anniversaries. This is a birthday party for a 13-year-old boy whose parents decided to treat him to this event, which was really special. And of course, our public observing programs happen on any clear night where there's enough of us to man a large crowd, and the observatory is not being used for some other purpose. And it's a roll-off roof observatory, so if you haven't been there, you can see this partial bird's eye view. You see the telescopes are inside the building. That roof closes. It rolls on to the building to protect it from the elements when it's not in use. And then when it's time for observing, we literally just press a button and all 4,000 pounds of that roof rolls right back. And it's a great way to have many people participate simultaneously. You've heard me talk about our planned planetarium. It's planned for our site, which is where our roll-off is right there in blue. The planetarium will be placed on this end with room for expansion into a larger facility if we decide to do that later on. Very traditional planetarium, dome seating for 65, or what we estimate for 3 classrooms. I guess that's sort of the metric that we use because we expect a lot of kids and schools to visit us on a regular basis. But additionally, you'll see just below that in this drawing is a state-of-the-art digital lecture hall that can be used for any purpose. We can clear it out. We can clear the chairs out and use it for dancing if we decide to do dancing under the stars. But we're really looking forward to having that in place. And again, our traditional planetarium would look similar to this. And here's just kind of a rendering of the way we imagine it to look in the future. This is not AI generated. I should have thought to do that, to ask one of those new AI apps to draw a planetarium as envisioned by the Adirondack Sky Center and Observatory. I've talked and written enough about it now. It should have a pretty good data source for collecting ideas on what we imagine it to look like. Our most recent initiative is actually pretty exciting. It's our Dark Sky initiative, and of course we've talked about Tupper Lake and why it's important. But there's 6 million acres in the Adirondack Park, and our plan is let me actually back up a little bit. Our plan is to start right in Tupper Lake and get the Dark Sky International, which is now their official name, to designate us as a dark sky community. And we will be the first in the Adirondack Park to do that. And my goal is, provided I survive and live long enough, is to expand that outward through all of the communities in the Adirondack Park so that we have a 6 million acre dark sky preserve. And aside from the value to nature and so forth of it, there's a great benefit to us as an observatory and for an astronomical center. We are the only astronomy organization in the Adirondack Park. But there's also a tremendous economic value to it for tourisms. People are seeking out dark sky recreation all over the country. I've done that myself. I've gone to other dark sky places. So it's what we're working on now. We've spoken with the town and the village. I've had some conversation even with the school districts a little bit, and we're well on our way. It's a long, tedious process. But luckily, Tupper Lake has really taken some initiative already to shield a lot of the lights that were installed on the streets in Tupper Lake. We have actually a board member on the Tupper Lake Planning Board, so any new construction gets put through the paces with them. And we seem to be getting a lot of positive feedback and a lot of good cooperation from the community on this idea. And again, right now we've submitted our initial application, and they'll conduct a review and they'll come up and talk to us and look around. And then we have some things that we'll be working on in the meanwhile, like an actual ordinance for lighting to be built in Tupper Lake, and for memorandums of agreement between us and the town and the village to preserve the night sky and kind of keep that going. So that may be the fastest I've ever spoken about us, but that's our Adirondack Sky Center and Observatory. That's who we are and what we do. I'm going to stop sharing for the moment and return back to regular place. We're honored tonight once again to have Jeff Miller. I'm going to reverse the order there, Jeff. You have St. Lawrence University, then Adirondack Sky Center and Observatory. If you don't mind, I'm going to just say Jeff Miller is a board member of the Adirondack Sky Center Observatory. He also works at St. Lawrence in the physics department. Jeff, I hope that doesn't bother you too much, but
Not at all.
it's my perspective. Jeff has been doing talks for us for a long time, has been an active member of our board, and does tremendous work with students there at St. Lawrence. So we're proud to have him as a board member, and we're proud to have him presenting tonight his presentation called "Blinded by Science." So I'll give it over to Jeff. Jeff, take it away, and we'll come back later and do a little Q&A.
All right. Well, thank you very much, Seth. So as Seth said, I've been teaching physics and astronomy at St. Lawrence for 35 years now, and have taken trips to plenty of observatories around the country. Tonight, I'm going to focus on a couple, only two of the observatories that I've been to. I was looking through my photos, and I, without exaggeration, have 12,000 photos just from those two observatories. So I hope you're not planning to go to work tomorrow, because we're going to be here for a while. So I called my talk "Blinded by Science" because as we make more progress in various fields, sometimes it interferes with other things. So I've stolen a couple of lines from two musical artists, and when more than smoke gets in your eyes. And this image that I'm starting with, I took that this summer at the Green Bank Observatory in West Virginia during our workshop in June. And that is not smoke, that is just morning fog. And it's Nice to get up early and take a walk around the telescopes at the observatory there when there's all this low morning fog. So let's start off by talking about just what astronomers actually are studying. What are we looking at? And it doesn't matter what your specialty is in astronomy, you are examining light. Now, to normal people, light is just visible light. Whatever I can see in front of me, I turn on a flashlight, I point a laser, and for countless millennia, that was how humans on Earth studied the universe. Everything we knew about the universe came from studying this very small section of the electromagnetic spectrum, which is what this is. Now, with technology advancing over the past, it's now 75 years, um, we have telescopes that can read at radio wavelengths. So the electromagnetic spectrum listed across the top here is longer wavelength and lower energy radio wavelengths. We can observe at infrared wavelengths, ultraviolet X-ray, and gamma rays. So the entire electromagnetic spectrum. So this slide, which I stole from one of my textbooks, shows that there are actually two windows in our atmosphere for portions of the electromagnetic spectrum to actually reach the Earth. Fortunately, one of those is visible light, or else we couldn't see where we were going. It would constantly be dark outside. The other are radio waves. So this is great because due to the low energy and long wavelengths of radio waves, radio telescopes are very, very large. So we want to have very solid supporting structures on Earth. Our atmosphere protects us from everything else on here. Some things we have to send a telescope up into an aircraft. I'll talk about that in 1 second. At other regions of the electromagnetic spectrum, you can see we've put satellites in space in order to be above our atmosphere so that we can actually read that form of radiation. And you can see the Hubble Space Telescope is just on the ultraviolet side of visible, and the James Webb Space Telescope is does a lot into the visible, but also mostly infrared. And the neat thing is, well, gamma rays, those are the shortest wavelength, highest energy form of energy in the electromagnetic spectrum. Fortunately, those do not reach the ground because if it did, we'd be living on planet Hulk. So fortunately, people aren't hulking out. Our atmosphere is protecting us from that. And on the left side, you can see approximately how high you have to be in order to observe at different wavelengths. Getting back to the aircraft that's here, there are two aircraft that we have used for infrared astronomy. The first one was the Kuiper Airborne Observatory, which was in operation for 20 years, from 1974 to 1995. And the next one, it goes by, astronomers love to use acronyms, SOFIA, the Stratospheric Observatory for Infrared Astronomy. And that was in operation from 2010 to 2022. And actually, if I remember to tell you, one of the former students of ours, who's now an astronomer himself, actually got a chance to use the Sophia telescope for some observational work and got to fly on the airplane. So it was very exciting for him. Okay, so now let's just focus on radio astronomy. So the radio wavelengths, that's what I'm going to talk about mostly today. We'll get back to some visible light stuff as well. So the next sequence of images I'm going to show you are from one large poster, and it is so large and there's so much detail in it, I have to break it up into sections so that we can actually see it. So here again is the electromagnetic spectrum listed here. You might notice it's in a different order from my previous slide. That's because this one is ordered by increasing frequency, which is across the bottom, whereas before it was by increasing wavelength. So it's in the opposite direction. So the next series of pictures I'll show you are from the radio spectrum in here, which again, we can reach here or it gets down to the ground, which is great because FM broadcasts, AM broadcasts, then we can actually listen to our radios as we drive. If you're still listening to old school radio. So let's zoom in on this and let's see what frequencies are allocated to different projects. Come on. There we go. So this mishmash, so the radio range of frequencies goes from 3 kilohertz, kilo is 1,000, to 300 gigahertz. Giga is a billion. And this would actually be one long strip, and it's broken up into smaller stacked sections. And all these color codes represent specific frequencies that in the US are reserved for certain types of airwaves. There's broadcast on here. Oh, and I don't have my glasses on, so I can't read this. Maritime, mobile, radio navigation, the ones that are there, we're going to zoom in on this in a second, but the ones that are very bright yellow, like there's a patch here, there's one here, and there's a few scattered down at the bottom here. Those are all reserved for radio astronomy. So I'm going to zoom into this particular section of the radio frequencies, and this is called the L band of frequencies, and they range from 1 gigahertz to 2 gigahertz, or as it shows along the top, it's also in megahertz. So you move your decimal place over 3 places, from 1,000 to 2,000 megahertz. And now it's a little bit easier to see. I was thinking of tipping this up vertically, but then it has to get shorter. It's impossible to read, no matter which way you have it. But now it's a little bit easier to read these bright yellow sections that are reserved specifically for astronomy. And some of these are actually reserved not just in the US, but all across the world. And that's great. But you can see how crowded it is. There's all sorts of allocations for other uses of the radio frequencies, and sometimes things interfere with our astronomical observations. So that's what we're going to be looking at today. I want to focus for now on one region of this L band, which ranges in frequencies from 1400 to 1427 megahertz. And the reason that that one is very important is because that is the frequency that neutral hydrogen actually emits photons. And it emits it at a frequency of 1420 megahertz, or in terms of wavelengths, 21 centimeters. So now you have to remember something about your high school science class, the structure of the hydrogen atom, our simplest atom, which is simply a proton which has an electron orbiting around it. And obviously, this is an oversimplified view of what a hydrogen atom looks like. Now, most of the time, it's in a high energy state where both the proton and the electron are spinning in the same direction. So if you take your right hand and you've got your thumb pointing up, you see that your hand is curling around counterclockwise. And so they're both spinning like that. But sometimes spontaneously, the electron can flip, and it flips so that it's pointing downward, which means that the spin now is in the opposite direction. And it turns out that the hydrogen atom is now going from a higher energy state to a lower energy state. And this is called the spin flip transition. It turns out it's emitting energy, it's losing some of its energy, and it emits a photon of light at a frequency of 1420 megahertz. But that transition in a single hydrogen atom is very rare. Remember, it does it spontaneously. Happens about once every 11 million years per hydrogen atom. Fortunately, there's a lot of hydrogen in our universe, so we can actually take advantage of it and use it as something that we can actually study about distant stars and distant galaxies. And that's the really cool thing. The nice thing about studying at radio wavelengths compared to visible wavelengths, actually, we observe at all wavelengths so we could put all of this information together. But at radio wavelengths, um, the energy, those photons can actually penetrate interstellar dust. Because if an object or a group of objects, a group of stars, are in a big dust cloud at visible wavelengths, we may not see them. But at radio wavelengths or at other wavelengths, they may be visible. So this spin flip transition is so important that on the plaques that are on the Pioneer and Voyager spacecraft that are journeying out past our solar system, they actually have a simple representation of that hydrogen atom making a spin flip transition, assuming that if any intelligent civilizations discover the satellites, they'll be able to figure out exactly, what's going on the rest of that plaque. This is part of a translation key. So let's take a look at an image in both visible light and radio wavelengths of a very famous object. Galaxy's name, it has a catalog name M87, also called Virgo A. It's a supermassive elliptical galaxy that has a jet sticking out of it. This is a Hubble Space Telescope image, and I forgot to put what year these images were taken in. And that it's actually a galaxy. It looks like a star because you can't see much detail, but there's, countless billions of stars in that galaxy. But it has this jet, very massive jet extending out a very great distance. And we think that that jet is caused by a supermassive black hole at the center of the galaxy. So this is what the image looks like at visible wavelengths from the Hubble Space Telescope. Here's what it looks like when it was taken with at radio wavelengths with the Very Large Array in Socorro, New Mexico. Now, if you want to really know a lot more details about this, when Eileen O'Donoghue gives her talk in a couple of weeks, she did her graduate school work at the VLA and studied M87 extensively. So she's the expert on that. So you can always ask her questions about that. So now, let's talk about sources of interference. So, what is the smoke that's getting in our eyes when we use our radio telescopes? So, we talk about this interference as we refer to as radio frequency interference, or for short, RFI. And here's a not complete list of some sources of RFI: wireless phones, Bluetooth, Wi-Fi, the wireless charging pad. If you have one of those induction charging pads that you put your phone on and it charges up without having to plug that in, that emits RFI. The spark plugs in your car and your lawnmower, they emit RFI. They can actually be picked up by large sensitive radio telescopes. Radar from airports, weather radar, satellites, power line transformers, and any unshielded electrical device. All of these are sources of electrical noise. And it's just going to get in the way of our observations with our telescopes. Now, this picture that I'm showing, this is from the Arecibo Observatory. I'll have some more pictures from Arecibo in a while. This was from our workshop in January of 2015, which I believe was our last workshop at the Arecibo Observatory. So I forgot it's been 10 years since we were down there. But you'll notice that it was in January. It was really tough. Somebody had to go to Puerto Rico in January, so we decided to volunteer to do that. So our group of astronomers would get together at Arecibo Observatory in January. We would do research. We would have little scavenger hunts, and obviously take a lot of photos. So there's Eileen O'Donoghue, so you can get a preview of what she looks like for her talk coming up in a couple of weeks. And you'll see a few of our former students in some of my pictures today. This is Evan Smith, who graduated from St. Lawrence in the class of 2016. Well, 2 years later, actually starting in the following year, we started having our workshops at the Green Bank Observatory in West Virginia. Going to West Virginia in June, definitely not as exciting as Puerto Rico in January, but it's still a nice excursion. You can see, I'm going to show you more pictures of the Green Bank telescope in the distance there. At this time, this is 2 years later, Evan was now a graduate student at University of West Virginia. And just a year ago in January, Eileen went to the American Astronomical Society in New Orleans and met up with four of our former students. And now Dr. Evan Smith is a staff scientist at the Green Bank Observatory. And Steve Goldman, remember I said one of our former students got to take a ride on Sophia and use it for research work. That's Steve Goldman. He works at the Space Telescope Science Institute. And these two students, Tyler Karazinski and Haley Perkins, are both currently graduate students in astronomy. Tyler is a second year student, and Haley, I believe, is her third year student. They're both working towards their PhDs in astronomy. So we're all very proud of them. So, why am I showing you all these family portraits? Well, it turns out that Evan, in his position now as a staff scientist at the Green Bank Observatory, is an authority on RFI. And so he and another astronomer just this year published a paper where they were studying RFI at the Green Bank telescope, the big one that's, I guess it's over my shoulder here, and attempts to mitigate any damage that it does to the data by various computer algorithms. And he published a paper, tried different mathematical routines to try and minimize the effect on our data. So this is a couple of pictures from their paper. The top shows the interference from an Iridium satellite that is, orbiting around the Earth. We'll talk more about those in a second. And so imagine if there was no interference at all. These would just be plain flat orange backgrounds. But you can see there's a lot of garbage in here. That's no good if you're trying to do astronomical observations. Likewise, this bottom one is airport radar, FAA radar from the airport in Bedford, North Carolina. So we can see that, these sources created by humans here on Earth, they can cause problems for radio telescopes. So, what can we do to try and quiet this noise? Because you saw the list I had before. There's sources of RFI all around us. What can we do? Well, around many large radio telescope observatories, they have a radio quiet zone where there are restrictions on the type of electrical equipment you can have. And so in West Virginia, actually, it covers West Virginia, a little slice of Maryland, and Virginia. There's a 13,000 square mile National Radio Quiet Zone, NRQZ. This was set up in 1958 to help facilitate research at the Green Bank Observatory, which is shown over here with this little dot. And also, there's a town called Sugar Grove where the NSA used to have some spy operations going on. It's a naval radio station. I'm sure they still do some spying there. But this area here is naturally protected by from external radio sources because it's in a huge valley. It's surrounded by the Blue Ridge Mountains. I think it's the Allegheny Mountains, and there's national forest. So there's not a lot unless you start plunking radio transmitters directly in here. It's very quiet. So when you travel down there, there is no cell reception at all once you hit the zone, the NRQZ, which means if you're using your phone for navigation, you have to make sure that your maps are downloaded so you can use it offline. You also really need to travel with a paper map, for those of you who remember what those are, just as a backup, just in case things don't work. And a few years ago, my wife and I did drive down there, and oh yeah, as soon as you hit the area, there's nothing. You get no cell reception at all. The quietest area where they have the most stringent restrictions is within a 10-mile radius of the Green Bank Observatory. So everybody who lives in there, and I looked it up, there are approximately 300,000 people who live in this region. Most of them live without Wi-Fi, especially in this area closest to the observatory. No Wi-Fi, and no cell phones. You know, if you want to use a computer, it has to be hardwired. Okay. And a lot of people flock to this area just because of that. They really like the silence. So let's take a look at the observatory itself. So this is a map of the Green Bank Observatory that shows some of the telescopes. There's approximately a dozen telescopes at the observatory. I think only about 5 or 6 are actually in operation. A lot of the other ones are historic telescopes. So where the most strict regulations are at the observatory are within this red zone, zone one. You can see this is where all of the telescopes are and centered on the Green Bank telescope. So no digital electronics. So any pictures that you take from inside the red zone, they have to be taken with, you've seen those disposable Kodak point and shoot cameras. They sell those in the gift shop at the observatory. Or if you have a really old manual camera. I've used a camera that I got as a graduation gift in 1988, and I've used older ones. Any film cameras that don't have any electronics, no automatic film winders or anything. It's all manual. So it's difficult to take pictures. I have to remember what it was like when I was younger. The zone two, which is kind of this gold area, which has the visitors' quarters, the science center, laboratories, workshops, and employee housing, it's less strict there. So, yes, you can use your iPhone to take pictures, but it has to be in airplane mode. And recently, they started telling us that you really need to turn off location services that, you know, so when you take a photo, even in airplane mode, your photo knows your location. It knows where it was taken. Those location services, they've found even that creates noise, emits RFI. So the last time we were there, none of my pictures that I took with my iPhone, none of them knew where they were. I had to manually set their location. So no Wi-Fi anywhere on site. And one other thing, glad I put my list here. No trackers. So how many of you have one of these Bluetooth trackers? I'm not sure if you can see an AirTag or some other device. These are a no-no. And even the key fob for your car. Now, this one for our car, has a presence center. So you don't even have to take it out of your pocket and you can unlock your door. That's fine. But what they tell you not to do is don't use the push buttons to lock and unlock your door because you're emitting an RFI signal. So one of the things I did before my last trip there, I was able to get some RFI bags. So when I got to the observatory, I put all of my so I put my key fob in there. I put all of the Bluetooth trackers that I have, and I got one in my briefcase. I got one in my wallet. I got one of my keys. Stuck them in here so that they're not screaming when they're sitting in my room in the visitors' quarters. So let's take a look at the observatory itself. The other thing that can only be or the only thing that can be driven into the red zone are diesel vehicles. Because remember, spark plugs emit RFI. That's a no-no. Telescopes can pick that up. So every vehicle that you see inside the red zone is a diesel vehicle. And I took these pictures. Actually, the one on the right I just took this year. Is right. They have an old checker cab sitting out in front of the science center, and this is in front of Grote Reavers. This is the actual telescope that he built in his backyard in 1937. So these are on display. But this checker cab, I mean, I remember vaguely going into Manhattan as a child and riding these things. They were just cavernous. They just seemed like they could carry a huge number of people. That was one of the vehicles that was used to get around at the observatory. In 2017, I think I took this picture of these three vehicles. I don't remember if the last one was a diesel, but certainly these two. These are International Harvester. They used to make vehicles, not just tractors, but they made basically what we would call an SUV from the 50s through the 70s. And this one in the middle, this ugly beat up gray one, the model name is a Travelall. So think of a Chevy Suburban. It's a vehicle just like that. And you could see at the time they were still being used. They still had license plates on it. During our most recent visit, these vehicles, I could see them way off in the corner, kind of in a, machinery graveyard. So I don't know if they use the old ones anymore. But what they use are these newer vehicles. Um, they have, diesel pickup trucks, diesel Jeeps, and I used to own one of these Jeep Liberties, and I know that CRD, Common Rail Diesel, so they have diesel Jeeps that they use to get around. So the whole point of a diesel engine is, unlike a regular internal combustion engine like you have in your car, where the spark plug creates a spark that ignites the fuel in the piston, and that's what basically makes the engine go. A diesel vehicle uses compression. So it compresses the fuel, and that's what ignites it. So it's not shooting off sparks, it's not emitting RFI, and you can drive diesel vehicles all over the place. So that's pretty cool. Even the tour buses that drive you around the site are diesel. So there's clattering diesels everywhere you go. The tractors that they use to mow the lawn, they have to use big tractors, and they're all diesels as well. So there's Eileen. You can see she's going to pop up in a lot of my photos today, listening to the universe whisper to us. So here's from inside the red zone. Now, this picture, you can see I'm outside the red zone. There's gates here, so you can't drive through unless you have a swipe card to open up the gates. There's some bright red lights that at night you can see them from a very great distance. Standing here, I took this picture with my iPhone, which is why this one is clear. And the first telescope you see is a telescope that's been on site since 1973. It's a 45-foot dish. And it was a portable telescope. It was designed to be taken apart and moved around the whole valley. And it was a test bed for an interferometer using multiple dishes to act as one large telescope. And so they were able to do tests and say, this very large array, which I believe is 27 separate dishes, can be used together, combined to make one larger dish. So that's what this telescope was used for. Now, these next few pictures, I took them this June. They were taken on film. They're definitely a little bit blurry. I think that's because I made the mistake of taking my film to Kinney Drug to get developed, and they didn't do such a good job, and they lost one of my rolls of film, so I won't be using them again. This is one of the old classic telescopes. Unfortunately, it's no longer used. The 140-foot telescope. It's been in use, or had been in use, from 1965 up until about 5 years or so ago. This was, and still is, the largest equatorial telescope ever created. And so an equatorial telescope means that it moves, or its movement will mimic that of the sky, and it mimics the rotation of the Earth. So you can see that this axis here, this is the polar axis. And if you were to shine a laser directly through the center at night, it would point at Polaris. And you can see there's this massive ring structure here that rotates back and forth. So I will get a view of the front in a second. And here's the huge dish, and there's the secondary smaller reflector. Just to get a sense of the size of this telescope, all the way down here at the bottom right, if you can see, that's the entrance door. And up here on this balcony, those railings are probably about 4 feet high. So this is an absolutely massive structure. You might wonder what this strange structure is here, this house on stilts. Well, when the telescope needed repair, they would spin it completely on its side so that the dish was perpendicular to the ground. And then it was directly at the top of this building so that the repair crews could stand there, replace instruments, make repairs, what have you. So here is a picture another picture that I took this summer of some, the nice thing about it is there's a long driveway. We would take breaks, we'd walk down, look at the telescopes. And again, you can just get a sense of just how massive that telescope is. And we're, several hundred feet away from it. So it's absolutely huge. Here is, the shining star of the Green Bank Observatory, the Robert C. Byrd Green Bank Telescope, or the GBT, as we call it. It has a dish that's 100 meters in diameter or 300 feet. So keep in mind, a standard football field is 100 feet across. So imagine something that is 3 football fields in diameter. It's huge. Now, unfortunately, usually we get a chance to tour the telescope, and they take us all the way right up here. And we're standing on top of the instrument room looking down into the dish. Unfortunately, they were scraping and painting the vertical arm here, and there was a lot of asbestos in there. So this was unfortunately as close as we could get to the GBT this trip. But again, for a sense of scale, and it's really tough when your photos aren't sharp, but if you can see this horizontal walkway here, so we would go up either in an elevator or you could walk upstairs. But this walkway has railings that were, probably about 4 to 5 feet tall, So it's huge. It's absolutely huge. So now we know that, especially in this day and age, we have a lot of electronics that run these telescopes. And they're all based in the control room, which is in the Jansky Science Lab. It is located 1 mile from the Green Bank telescope. So that's quite a distance, but we still need to keep all that machinery quiet. So this is where the operator will sit. There are just computers everywhere in this room. So here's one location, and there are for different telescopes and multiple screens for one telescope. And if you turn around, there's more screens behind you. There's got printers. They've got who knows what this giant box is back here. And behind this glass window, there's a whole bunch of computer servers. And there was other computer servers that they told us don't take pictures of because that's, super secret stuff. It's like, okay, I don't think it was this server, but maybe. Who knows? Maybe I'm spilling state secrets. All of these things are going to emit a lot of RFI. So, how do we keep it in? And you say, wait a minute, look at this. In the control room, they have this big, beautiful picture window. Glass isn't going to do anything. And there's actually a little balcony out here. You can see a pair of, giant binoculars, and you can see the GBT off in the distance. Again, that's 1 mile away. So that gives you a sense of just how big that structure is. So why would you put a big window in a place where you're trying to keep any electrical noise in? Well, first of all, if we look from another angle at that window, it's actually a series of windows and a door that, take a look at this door. This looks like something you might see on Fort Knox. I don't know if you can tell, there's a really long handle. You have to really, boom, crank the handle, kind of like the old handle in voting booths. Remember, when you turn that handle to submit you vote, you knew you voted. Okay. It was something huge like that. But look at all the metal structure around here and all this copper. Everything is grounded, everything is shielded. And the glass itself, when you get up close to it, has this fine mesh covering the whole thing. I was hoping when I took this picture to get the mesh and the GBT in the distance and focus. There's no way that's going to happen. But this is going to help keep in that RFI interference. Now, think about this. You've looked at your microwave when you're, cooking your oatmeal in the morning. You can see what's being heated up inside your microwave, but there's like a mesh surface on it, right? You can see through it, but the microwaves can't get out. That's because the microwave wavelength is somewhere between 3 centimeters and multiple centimeters. It's very, very long. So microwaves can't get through that little mesh that's in your microwave oven door, but visible light, which is at a much smaller wavelength, can actually get through. And it's the same idea here. We can see through this window, but any radio interference being emitted by our electronics stays inside the building. Very cool. Even the door itself to get into the control room looks like a door that belongs on a vault. I should have taken a better picture of this, but look at the edge. This is a huge, thick door. It also has one of those giant handles on it to close it. And you can see there's copper everywhere. Everything is grounded. The light switches are attached to a big piece of copper. The exit sign is attached to a big piece of copper. Nothing is getting out of this building. And apparently, if you call the Universal Shielding Corporation, you can get a door like this too. Just give them my name. They'll give you a good price. So let's talk about the actual interference that we have seen on our radio telescopes from terrestrial, from human created sources. So we're going to start with the discovery of fast radio bursts, FRBs. These were first discovered using a telescope known as the Dish, which is at the Parkes Observatory in Australia. If you ever saw the movie The Dish with Sam Neill, the dish was used as to transmit some of the original video signals from the moon when the Apollo 11 astronauts landed on the moon in 1969. And if you get a chance to see that movie, it's a fantastic movie. Slightly fictionalized, but it's very entertaining. So this is a 64-meter or 210-foot dish. So there were some astronomers who were going back and looking at some data and realized that they were seeing in some of the old data some transient radio waves that would just pop up for an extremely short period of time, from fractions of a millisecond up to 3 seconds in length. And that's a really, really short time. And that's why it's called a fast radio burst, just very, very short time. We initially would think or thought that, based on other measurements, that it was some extragalactic source with huge amounts of energy. It's just releasing so much energy in 1 millisecond. So a millisecond is 1,000th of a second. So 0.001 seconds. It releases in that short period of time as much energy as the sun does in 3 days. So huge amounts of energy in extremely short periods of time. The problem is, these are great. These are very exciting, these FRBs. At the same time, they were seeing other signals that looked the same, but due to some other measurements, they said, wait a minute, these are terrestrial in origin. There's something on Earth creating these. And so these images show some test images when they were trying to figure it out. It's like, no, wait a minute. If some of these images or these FRBs are actually created by something that humans have done, well, that kind of calls into question the actual FRBs. Well, maybe they're not real. Maybe we're just misinterpreting it. So in 2015, they did some further studies and they were taking some measurements. So these three graphs are three separate incidents. So you can see it's on 3 separate days where some transient radial pulse. And here, notice the scale is in milliseconds. So this is 600 milliseconds. This would be, about 650. This total scale is about, a third of a second in time. There's obviously some streak here. Frequency is on the vertical axis. So something is happening here. We can see the energy flux. There's some amount of energy coming from it. But these did not indicate being from another galaxy. So they called these perytons. Periton it's not even from mythology, but it's a fictional character. It's a winged stag that casts the shadow of a man. And they said, okay, well, it seems to be something, but it really isn't. I think that's why they came up with that name. So they started collecting data, they started doing tests, and then they went back and looked at the original data and found that when they plotted the number of events of these original peritons from that original data set over the time of day. So this is in coordinated universal time. So here we have noon, here's 8 a.m., here's 8 p.m. They found that there was a great number of events in the middle of the day and and then they tailed off towards the evening, but nothing in the middle of the night. So it's like, okay, well, what is going on? After further examination, they found what the problem was. At the observatory, there were three microwave ovens. Two of them they suspect of being the culprits. They were at the time about 30 years old. One was in a staff break room, the other was in a cafeteria. If somebody was heating up a cup of water or what have you and opened the microwave before the timer beeped, it turned out that there was enough of an extremely brief pulse that the telescope would pick it up. So it turns out, so what they did this testing, that's what these are from. They just kept heating up cups of water, cups of water. And they found at least half of those spurious signals were due to those old microwaves being opened up before the cycle was completed. So one of the things at the Green Bank Observatory that they do with their microwave ovens is they are all in an extremely heavily insulated box. And so after you put your stuff in, you close and lock the door while it's running, and everybody is under orders. You do not open the exterior door um, while it's still running. You have to wait and finish. And notice they still use, the very cheap old style microwaves that don't even have push buttons on it because with push buttons you have more electronics. That's just going to create more noise. So this one is in the corner of the control room, sitting right by the window. And this microwave is in the staff cafeteria. I don't believe they have any microwaves in any publicly accessible areas. So everybody knows exactly how to use them. Although, frankly, in all the trips I've taken down there, I've never seen anybody use the microwave. So they probably don't use them that often. Oh, satellites. That was one of the things on the list that actually can interfere with our telescopes. Well, let's get a sense how many satellites are there that are orbiting the Earth. Well, this is a screenshot from a website, Satellite Tracker 3D. We're going to look at this website in a second. It gives you a sense of, holy smoke, there's a lot of satellites out there. Currently, there are approximately 12,000 active satellites orbiting the Earth, some in near Earth orbits. That's why that's the Earth in there. It's covered in a cloud of satellites. Some of these here are in geosynchronous orbit, and there is some, farther out that I zoomed in a little bit too much on this. If we consider not only the satellites, but all of the stuff, all of the junk that is orbiting around the Earth, there's approximately 45,000 objects. If we go to the satellite tracker itself, and you can make a free account here or log in with your Google account. I did that. And so now Google has all of my information. But this is a fascinating website because you can click and drag and see everything. You can zoom in and out. And if we zoom in here, and you can, if you click on an object, you can get information about it. You can see what its orbit is around the Earth, all kinds of cool stuff. But the thing I want to show you first, we'll come back to this later, is if I show just the debris that's hanging around the Earth, that is what it looks like. That is all the stuff, all the junk that is floating around in orbit, spent rocket boosters, dead satellites, things that haven't burned up in our atmosphere. You can also select different types of satellites. We're going to do that in a few minutes. We'll come back to that. But it's really a fascinating website. You can spend just hours and hours and hours going through here. Okay, we'll come back to that in a little bit. So let's take a look at how some satellites have interfered with radio telescope observations. And here is a picture of the Arecibo Observatory, which first went online in 1963 and sadly came to a horrendous end in 2020, as many things did on the Earth. In case you're not familiar, it had a failure in some of the support wires and the entire structure collapsed. Now, it was a telescope that was so big, it was the largest single dish telescope in the world until about probably 15 years ago when China built a larger one. The dish itself is so large, it is a 1,000 feet across. So remember I said that 100 feet, right? Or so 100 yards or 300 feet is the size of a football field. So, divide 1,000 by 300. You've got a bunch of football fields going in here. It's absolutely massive. Hanging from these support cables is the platform, which weighed 900 tons. Yes, that's not a typo. 900 tons, absolutely massive. The dish itself is so large that I was looking through my 10,000 photos of the observatory. I didn't have any that showed the entire dish because it was too big, and at the time I didn't have a wide enough angle on my cameras. So here's a couple of pictures that I actually took, and that shows the platform. I always like taking a picture that showed its shadow on the dish. And that whole platform was 450 feet above the dish. That dome there, it's called the Gregorian Dome. That's where it housed most of the instruments. It was 6 stories tall. It was an absolutely massive structure. And I forgot to label it. You might see a rod hanging straight down. That was a 440 megahertz transmitter because not only did Arecibo receive radio wavelengths, it also transmitted radar signals, and it mapped the rotation of Venus, mapped the rotation of asteroids, did a lot of radar work as well. And supporting that 900-ton platform were 3 of these absolutely massive towers, 350, 370 feet. They weren't all about the same height. So absolutely huge structure. Again, just to give you a sense of how big that structure is, here's a picture I have, and that's a couple of people on the walkway on there. So truly massive. So remember this Gregorian dome, 6 stories tall. So it also had a lot of electronics in the control room. Things were shielded, not as much as they are at Green Bank because it was only one telescope and we knew which wavelengths were being observed. So they even used Jeeps to get around that had spark plugs in it. They didn't even go with diesel engines because for this instrument, that wasn't an issue. It is at Green Bank, but it wasn't at Puerto Rico. So this is another student we took down, Heather Cutler, who is now a science teacher at high school, I think in New York somewhere. So here's the instrument that we use. So inside that Gregorian dome, we had the Alpha instrument. Alpha, another acronym, stood for the Arecibo L-band feed array. And it was a 7-pixel radio camera, which was huge at the time. Typically, radio cameras, radio detectors, just 1 pixel. We were able to get an instrument that had 7 of these. So it really increased the resolution, which means we could observe our universe in much more detail. So the picture on the left is from a student, Sean Golly, who currently he deals with computer programming. Sean was very a fascinating student. He was legally blind, and he went up onto the telescope and, hustled all over the observatory, worked on the workshops, did a lot of the data reduction because he could see a computer monitor well enough. And the picture on the right has Heather again. And one of our observing runs, we were down there with a student and a faculty member from Colgate. His name was Phil, and I forgot to look up his last name. But you can see the underside of this alpha instrument. So, what did we actually see when we were looking at our computers? There were many displays that we would switch between when we were actually observing. And oops, somehow I drew some lines on here. And while we were observing, one of the displays that we would keep up was what we called the waterfall display. And it showed everything from all 7 cameras, all 7 pixels on there. And basically, we use this to let us know that everything was operating with the telescope properly. And I'm just going to take a look. Here's one up close and just zooming onto one. And we could switch between individual ones. So along the horizontal axis, we had frequency, and we can see it from 1340 to 1420 megahertz. And along the vertical axis was time. And you'll see up here it's 141, and down here was 142. So what would happen as we were taking measurements is the display, the waterfalls would actually go up as information came in as the sky was passing overhead. So if everything was going okay in this display, we would see mostly orange. Now, there's a couple of vertical lines on here you might spot. Apparently, I scratched some lines on here. My apologies for that. But this one on the left at 1350 megahertz, that was created by the airport radar in San Juan. And we always felt comfortable when we saw that operating because that meant we were going to be able to get home. We didn't have to stay in Puerto Rico, although there were worse places to stay. Now, there's a fainter one on the right side that you might be able to make out. Notice that it's at 1420 megahertz. Ooh, that's the emission line from neutral hydrogen. So, what is it that we're actually observing here? Well, it turns out that that is hydrogen from our own galaxy. That's the Milky Way galaxy that we're looking at, because obviously we're looking through the Milky Way galaxy in order to see more distant galaxies. So, once again, here's what the display looked like if everything was normal and operating as it should be. And sometimes you would see this, a pair of dark bands. And remember, the time is scrolling up. So all of a sudden you get these dark bands just appearing and going through. And it's like, uh-oh, what button did I touch? Did I just break something? Well, unfortunately, that's not what, or fortunately, I should say, that's not what it was. We didn't break anything, but it's what we call a GPS burst. On the GPS satellites that are orbiting the Earth is a nuclear detonation detection system called NUDET for short. And so periodically, the GPS burst would come out as a test to make sure that the system was actually working. There was um, a strict limit on how long and how often those bursts would happen so that it wouldn't interfere with radio astronomers. And if they needed to actually do some more extensive testing, they were supposed to schedule it with observatories. And it was only once where we saw a whole sequence of these going by, and we had just had to stop observing for the night. But most of the time, it would be one marching through. So, as one of the PIs for our project, the principal investigators, Martha Haynes, had written in our observing manual that explained some of these sources of RFI that we might see while we're observing. She wrote, fortunately, GPS/NUDET bursts result from system tests and do not mean that an above ground nuclear event has taken place. So you don't need to dive under a desk. That is a joke to us old folks. So everybody who is a boomer probably remembers the duck and cover drills, especially if you lived in New York City. I went to school in Queens for kindergarten and first grade, and we had these duck and cover drills in the hallway. You had to hunker down away from glass door, glass windows, glass panes and doors. And if you were in the classroom, you had to get under your desk because hiding under your desk was definitely going to protect you when the commies nuked Manhattan. We all felt much safer doing that. So, what did that actually look like in the raw data itself? So, as we collected that data, so remember I said the waterfalls plot didn't show us any galaxies that went by. We had to look at the data later, and we had to go through a process called flagging, where we would mark off areas that would be ignored by the next series of steps that we could actually observe, use to reduce the data to come up with something that was usable so that we can actually continue with our calculations. So in this particular image, there's not much notation on there, but the frequency goes along the horizontal, the bottom axis. So we see our two familiar friends. We have the San Juan Airport radar and hydrogen from our galaxy. But you might notice I also have this kind of S-shaped elongated area. That is from a galaxy that we actually observed. And most likely, that is a spiral galaxy that we're looking at on the edge. So I have my little uh, model galaxy here, which is basically a ping pong ball glued to a CD, a compact disc. And if I tilt it a little bit, remember, galaxies are rotating. And so if you remember what the Doppler effect is, right? If you watch a car race on TV, cars go, meow, right? As it goes by, the pitch of the engines change. Same thing happens to light in general, not just sound waves. So that if you have one side of the galaxy coming towards you, that will make it the light shift to shorter wavelengths, whereas the other side is shifting to longer wavelengths because it's moving away. And that's what causes this slight squiggle because it's not appearing all at the same wavelength or all at the same frequency. So that's pretty exciting. What happens when you have a GPS burst? That's what it looks like. You end up, this particular data set had 3 GPS bursts in there. So any data that's there is unusable. And you can see that there are red boxes. Somebody had already flagged these. Yeah, you need to totally ignore that stuff. That's no good at all. Fortunately, most galaxies would appear kind of in this region, but if this occurred where there was a galaxy of interest, you've lost that observation. You just have to hope to be able to observe that galaxy again another night. So, satellite streaks. Well, on photographs, we've been having that problem for it's now 68 years. Just a few days ago was the anniversary of Sputnik 1 being launched into space in 1957, October 3rd or something like that. So there's been satellite streaks on photos for a very long time. And we've known about this. And okay, so astronomers have dealt with this. This picture, I found this picture in the next one on an article about how to recognize satellite streaks compared to meteor streaks on a photograph if you're taking astrophotography. This again, these two are iridium flares. So they're from the iridium satellites, and they apparently flared at the same point. We're going to see a picture of an iridium satellite in a second, but the original ones were designed with a big flat reflective surface on it. And there are certain times when they're in its orbit where you get a bright reflection down on Earth. And these iridium flares are well known, and you can look them up when one actually occurs. I did that once. So standing out on my driveway, and it's like, oh wow, that's actually pretty cool, to see it. All right, so it would ruin any data you were trying to observe on there, but it's not quite catastrophic. Here's another image that shows the space station passing overhead, so it makes a larger streak. Here's some random satellite that makes a smaller streak. And then this one in here is just a rogue meteor that's actually passing through. Okay, in visible light photographs, yeah, we've had to deal with this for a while. So, but we know about these satellites, these Starlink satellites. Now, they have done their purpose in terms of bringing internet to a lot of areas that didn't have internet access before. Okay, that's great. However, why are people complaining about these Starlink satellites? Well, first of all, let's take a look at the Iridium satellites. And this is an example of one that's at the, I think, one of some Air and Space Museum. But these big reflective panels you can see is what would reflect light, sunlight back to the Earth. And there's only about 80 of them. And the Iridium satellites are communication satellites. So telecommunications, I think they even provided some internet service. What about the Starlink satellites? Here's an image of a whole cluster of these satellites on the rocket just before being deployed. So the newest number I have for the number of Starlink satellites as of September 25th was just about a week ago. If you're ready for the number, 8,475. And some of those aren't working, but most of those are actually working. That's a lot of satellites. So if we go back to our satellite tracker, what we can do is we can show a few of the different satellites that we have. And so let's first of all look at our GPS satellites. I'm going to click Navstar. Those are the GPS satellites. And this is what helps us, figure out how to get from home to, the Five Guys downtown without getting lost. Okay. So those are our Navstar satellites. The Iridium satellites, you can see, are in a close Earth orbit. And there's about 80 of them. And, again, we can select each one and show what its orbit is. All right. And you can get information about it as well. Let's take a look now at the Starlink ones. I'm going to turn this off, turn this back on. Those are the 8,475 Starlink satellites. Let me zoom in here. Look at this. Look at this. And, you can flip through. I like this random satellite. I'm just clicking through and it's just showing you the orbit of these things all over the place. You can see there's a lack of them up near the northern hemisphere. And it was something I found near the southern hemisphere. And you see there's a line of them. So that's a newly deployed train. So if you've seen them pass overhead, they initially all travel in the same orbit until they spread out in their own orbits. And if we zoom in close enough to these, let me get one here. Can you see that they're moving? This this website gives real-time tracking information about all of these. So while the Starlink satellites have been a boon to people who could have internet access now, but couldn't get it before, they have been a nightmare for astronomers. This photo from the astronomy picture of the day, the astronomy picture of the day, the image appeared in 2021, but the picture itself was taken in December 2019, which is shortly after the Starlink satellites were starting to be deployed. So this is the Orion Nebula with all these streaks through it. So on photographs, so making imaging, and I know Seth had mentioned something about it, it's been much more difficult. So the question is, how do these Starlinks or do these Starlink satellites cause problems for radio astronomers? So this article, which was from almost exactly 1 year ago, October 25th, 2024, this is a news release from NRAO, National Radio Astronomy Observatory, which Green Bank Observatory is part of. It says over 99.5% of residents in the National Radio Quiet Zone can now receive satellite internet service. So this image, it's a little bit hard to understand. So the black line here is the quiet zone, and the previous restricted area. So I think outside this area, people there was a less restriction. People could get satellite internet, but not within this red line. And so here's Green Bank Observatory. Here's that Sugar Grove Naval Station. Still, this area is still restricted. But what they are doing is they have been working with uh, people at Starlink, at SpaceX, in order to test whether they can actually use the Starlink satellites for satellite internet. And they've been working for since 2019, since the satellites were deployed. And 1 year ago, it says SpaceX will begin a 1 year assessment period to offer residential satellite internet service to 99.5% of residents within the NRQZ starting October 25th. This was last year. And so that's what these black areas were. This is the assessment period. So that was 1 year ago. Haven't heard what the results of that was. So maybe the Starlinks don't interfere with radio telescopes. But I also found this article from July of this year. Scientists analyze 76 million radio telescope images, find Starlink satellite interference where no signals are supposed to be present. So what they found is that about 30% of these 76 million images had some emission from the Starlink satellites at wavelengths that are supposed to be protected for radio astronomy. So I don't know what the final answer is, but it's definitely something that needs to be investigated further. And I meant to send a message to my former student, Evan, at Green Bank and say, hey, what do you know about this? And I never got around to do it. So one final thing. I know we're time's going on. We're going to wrap up here. I'm going to show you one final telescope and one final source of interference that astronomers have had to deal with. So this telescope was at the Green Bank Observatory. It used to be called, Green Bank used to be called the National Radio Astronomical Observatory, NRAO. And this was a 300-foot radio telescope. At the time that it was built in 1960, I believe, it was the largest steerable radio telescope. So it wasn't fixed like Arecibo, but it wasn't like Green Bank where you could move it around. The Green Bank telescope, all it could do was go in one axis back and forth, but it could steer it. It was actually absolutely massive. Remember, I showed you a picture of an international travelall, that SUV. It kind of looks like a Chevy Suburban. If you can see in this tiny picture here, there's one parked outside of the control room in front of this telescope. So I like to show this picture because this reminds me that some 40 years ago, some young budding astronomers actually visited the observatory and took a photo in front of this telescope. And if you haven't recognized the handsome devil on the far left there, that was me some 50 pounds ago. I know it's a little confusing. It looks like I'm wearing a helmet, but that's actually my hair. I don't know what the deal is with those glasses. And I think those were glasses that got darker by themselves. I think they could withstand a nuclear blast. That's also when I didn't have to suck my gut in order to be able to tell if I was wearing a belt. So anyway, in 1985, we were coming back from a conference in Charlottesville, Virginia, an American Astronomical Society meeting, and our professor stopped here so we could look around the observatory. And we got a tour from Rick Fisher, who we didn't know at the time. My professor did, but we didn't know it until we got home. And he's a very famous astronomer. And he showed us all around the observatory. Now, I like showing this picture because when I show this to my students, I remind them that in this picture, I was their age and that they're looking at their future. Very few of them laugh at that, although I think it's hilarious. One more picture to show. 1985, visited the observatory. A few short years later, unfortunately, that telescope collapsed. just totally crumbled. Is it a coincidence? I know I have a magnetic personality. I tend to do these things to massive structures, but fortunately, we have real hotshot journalists who actually figured out what the problem was. Space aliens. They zapped the telescope. That's according to the National Enquirer in March of 1989. And the reason they did that is they zapped it with a powerful laser to keep scientists from monitoring their activities in the Northern Hemisphere. They even quote a Swiss astronomer named Peter Voissard. There is no astronomer, Swiss or otherwise, whose name is Peter Voissard. Everybody who has read this has Googled him, even recently. And no, they just made up a story, but it sounds great because that's what sells papers. So I hope you have enjoyed this little journey into our exploration of radio frequency interference, things that get into our eyes from the advance of technology, and what our efforts are in order to keep it at bay so that we can try and examine the universe as it is. So I will stop sharing, and if anybody has any questions, I would be happy to answer those for you. I hope you were able to see the whole presentation. I am just looking at an image of myself through the whole thing. So
Yeah, it came through fine, Jeff. Thanks so much.
excellent, excellent.
I know that I complain sometimes about the size of the telescope that I have to move from one room to the other. Yeah, I'll stop doing that from now on.
Yeah,
Just out of respect.
I know, I know. I'm complaining these days about moving our old 8-inch Celestron. It's just like, oh God, do I have to schlep this? So,
Yeah.
and but yes, that satellite 3D satellite 3D website. Holy smoke! I've been playing with that a lot, so it's very cool.
Yeah, after you showed it to me the other day during our rehearsal, I lost the next few hours of my life on that. So that's great. What questions do we have any out there from anybody? There was a question earlier about the scale from Tammy about the different scales comparison of visible to radio in Virgo A. I don't know if that's still
Yes, they are supposed to be, those images are at the same scale. So it's not one is zoomed in or the other. So
uh,
yeah, so you can just see at that particular size at different wavelengths, and you could find lots more images of M87 at different wavelengths, and a lot of them show that jet, and you see different structure at different frequencies or different wavelengths. And that's the beauty of astronomy, that since we can study at all wavelengths, it really gives us a more complete package of what we're doing, or what's happening in the universe. Because that's the thing we have to remember. With very few exceptions, we can't travel very far to go to these distant stars, go to these distant galaxies and look at them up close. So everything we know is from the electromagnetic radiation that reaches our Earth or close to it.
mhm. Excellent. A couple of other questions. How many more Starlinks are planned?
I was going to look that up and I didn't get a chance, but I'm sure they're probably still pumping some up. And some of those, like that number 8,475, whatever it was, there's was it 100 or 200 of them, like aren't operational. So I'm sure they have to replace them and send more up there. But it's
What
something.
what's fascinating to me is, even getting out of Earth's orbit, to visit the moon or to go, any of our missions, NASA missions, just to navigate that cloud of debris to get out without hitting something is got to be
Hmm.
that's got to be a nightmare.
Exactly. Exactly.
Do power transmission lines that are above ground radiate radio power RFI?
Yeah. Yeah. And I think a lot of the power cables at the observatory are buried. And I was going to show one additional picture, and I just like, oh, I already have too much. Um, I took a picture of the lights that are outside of the visitors' quarters. So we're very concerned at a radio observatory with keeping it radio quiet. But light pollution? There are floodlights that they have pointing right at the dorms where we're sleeping, unshielded. I mean, just bare fixtures that are just sitting there. And I was going to include that. It's like, oh, I don't want to add more pictures, but yeah. And it was the same thing at Arecibo. You walk around and there's just bright lights in your eyes because we're not using optical telescopes. It's fine.
Mhm. At our roll-off observatory, we have security cameras that use infrared. And I've got to remind myself when we're doing imaging up there to that actually does bleed onto the camera sensors. So
Oh, right,
that
right.
we get a whole lot of what looks like hydrogen in our images. But it's just uh, we have two different ideas of noise and pollution.
That's funny.
Well, this has been great, Jeff. Really, really appreciate it. It's like, going back in time to some of those that 1963 or 1965, that is really spectacular to think about that. We were doing this stuff, what seems like not that long ago, but by the same token, that's really a couple of generations already.
Hmm.
Yeah,
Yep,
it's a
yep,
long time ago.
exactly.
Yeah.
That's right.
So,
And just the fact that, I mean, radio astronomy has only been around since, the 19 late night, to late 1930s. So, it's yeah, so I mean, God, I said 75. No, it's like 80, well over 80 years
yeah,
compared to visible, like visual astronomy, which as soon as we opened our eyes and started looking up,
right.
we've
Yeah.
been able to observe the sky. So
Yeah.
yeah, that's remarkable.
What's your next trip? Do you have another trip planned?
To an observatory, probably not until I go to Green Bank in this following June, if I go into that.
Yeah.
Um, but yeah, and I haven't had the best of luck with observing using Green Bank because with the Arecibo telescope, Eileen and I got to be really good observers, and we would observe on site, and we could observe remotely from St. Lawrence. And we did a lot of observing during the initial phases of the project. And then when it came time to use Green Bank, it seemed I was like, okay, I'm going to get trained to be an authorized observer. And so we went down there for a workshop. Okay, I've read all the manuals. I've done all the test routines. I've done through everything. Oh, the telescope is broken. It's down for maintenance. Can't do it. We'll try next year. Something else came up. And this last time, um, they were painting it and they've had that before. So I haven't mastered even done much observing itself with Green Bank.
Mm,
And it's just like, yeah, it's getting too close to the end of my career. I'm getting tired. So yeah, I won't probably reach the level of proficiency I had with Arecibo, but
yeah.
and that was such a shame when that collapsed.
That was a dark day. I think I sent you a
And
sympathy
so it
card.
was.
Yeah.
Yes.
All right. Well, thanks again, Jeff. Great talk.
Great.
Fascinating to look at the size, really. Just the size is fascinating, let alone the
Hmm.
technology in there, but
Right. Right.
fantastic. So
Great. Thank you.
with that, I would invite everybody to check out our schedule. Eileen O'Donoghue is next up in just a couple of weeks. Well, actually, not even that long. It's maybe just a week and a half or so. So check out our schedule online. call the office, subscribe to our newsletter. You'll get the email blasts of when everything is happening, including opening of the observatory for public observing programs and our planetarium shows. Everything that's going on is news that's fit to print in our email blasts. So with that, thank you everybody for joining us from wherever you're joining us from, and I look forward to seeing you again soon. And thanks again, Jeff, for another great talk. Always look forward
Thank you.
to this.
Yep.
All right.
Thanks.
Good night, everybody.
Good night.